Good afternoon, everybody, and welcome to this Avantor's webinar on sustainable approaches for your liquid chromatography workflow. Before the session starts, I'll just do a bit of housekeeping. So we will send you the recording following the presentation. Please submit your questions at any time into the question box in the GoToWebinar app. However, we will keep the questions to the end unless they're kind of general points that we can answer during. But any technical questions we will do in the Q&A session. We will send you a certificate of attendance following the webinar. And if you have any questions after the session, then please feel free to contact us webinar@avantorsciences.com. So I'd like to introduce today's speaker, Arianne Soliven. She is a product specialist at Avantor for the self-manufactured LCMS products. She obtained her PhD in Australia with Professor Andrew Shalliker and has more than 15 years of chromatography experience. She's worked across the world with leading academics, including the eminent Professor Georges Guiochon at the University of Tennessee and Professor Peter Carr at the University of Minnesota, and she has more than 50 peer-reviewed articles published. She's worked in the manufacturing sector with advanced materials technology and in the pharmaceutical industry with Novartis. She is currently an honorary adjunct fellow at Western Sydney University, Australia, and an editorial board member for Chromatographia. She's really passionate about sustainability, supporting diversity, equality, and women in science. So with that as a quick summary of all of her expertise, I will now hand over to Arianne.
Thank you, Cass, for the lovely introduction, and also thank you to everyone tuning in today. And a really big thank you to all of the team here at Avantor. Thank you for helping with all of the material that I'm really proud to share with everyone today. Okay, so the outline of today's webinar will be sectioned off into 3 different sections. The first one will be to introduce some definitions of sustainability and go into some approaches with respect to liquid chromatography. The second section, we will look closer at solvent management decisions as well as column selection decisions. And the third and final section, I would like to share with you some really nice examples on how to translate your original methods into aligning it with more sustainable liquid chromatography workflows, as well as some applications that really highlight some really nice tools to do so. And overall, I'd really like to give you some key takeaway messages in alignment with sustainable LC assays and really highlighting to you really nice and easy choices with respect to your solvent management, as well as utilizing reduced column formats that either are packed with fully porous particles or superficially porous particles. And with that, I'd like to begin the first section. So I'd like to actually begin with how we define sustainability here at Avantor, and it is based on 4 different pillars as shown here, and they're all in alignment with science for goodness, and they include people and culture, innovation and environment, community engagement, and governance and integrity. It is important for me to also share with you the different stages of a circular product life cycle shown here, and also express to you that we are going to focus on the use in this webinar. There are different, and I'm going to list here only a few examples of different chromatography approaches. There's not enough time to share with you all of them. However, these are really nice and different sustainable considerations for you to align your chromatography lab to sustainable aspects. The first one is going to be related to reduced materials used, and that's specifically related to your column format with respect to the column length as well as the internal diameter. And the production of these tools use less stainless steel as well as less stationary phase material. They are great because the operation of these tools for your LCMS assays, they allow you to reduce the solvent, specifically the mobile phase solvent, with its consumption and its waste production. There is a drawback, and that's that's going to be addressed by the manufacturer, and that's the increased difficulty in packing those columns, particularly with the smaller internal diameter products. Another approach that you can consider, it's a little bit more specialized, and it fits under this title or header, recycling and reuse solutions. That's recycling the mobile phase solvent. Another approach to reduce that solvent consumption and waste production. However, it does require a special setup, and that's for the assay to redirect the column effluent, anything exiting the column, to be redirected back into the column inlet. And in saying that, it is probably highly recommended to apply this to specific applications where mainly it's isocratic because you know the mobile phase composition. Also, you can target the parts where there are no eluting peaks. So when you look at your final data, you can understand the final chromatogram in an easier way. And the final one that I'd like to share with you is the productivity. So by developing faster and more high performance or efficient LC assays, it will assist your lab with reducing the time as well as the consumables you spend every day in the lab. And there are different strategies, computational software that help you with method development, different decisions, as well as retention modeling. Or you can look closely at your column selection choice. Specifically, we're going to focus and hone in with this webinar at considering UHPLC columns as well as the systems, also superficially porous particle column technology also to help you increase the productivity of your lab. And with that, I'd like to start the second section of this webinar, looking at solvent and column selection decisions. And I actually want to begin with a mobile phase because there's not enough time to touch on all points, but I do want to spend a bit of time with a mobile phase or the solvent that you use every day in the lab. It may be difficult for us as analysts to implement an alternative or more environmentally friendlier solvent with our protocols. However, because they may require revalidation, and of course the peaks are going to move and shift with a change in your mobile phase. However, there is another approach, and it's one where we take a step back and we look at how we manage the solvent that we order and that enters our laboratory space. So in this slide here, we specifically are talking about the single-use glass bottles that we typically use, which may come in 4 liters or lower volumes. So these are what we commonly use and what we usually are familiar with. However, in order for the manufacturer to send that to our labs, it does require additional materials to package, ship in a safe manner and not introduce a safety hazard with broken glass before it arrives to our lab. So the alternative that I'd like to bring your attention to is these returnable stainless steel barrels. They are available in larger volumes, so you can also decrease the frequency of your purchases and also decrease the greenhouse gases associated with the shipping. So they're available in 10, 30 and 185 liters. So great alternatives. It does require a special setup, and that's in order for you to withdraw that solvent and into your laboratory space. I've been told, and this is a really neat aspect of this alternative, you can, and there has been labs that are specially set up to connect the solvent direct to the system, which is really great. I wish I could have been exposed to that laboratory environment myself when I was in the lab. However, if it's not directly connected to your system, it can be directly connected to your lab, so you can aliquot it in a more manageable volume for your sample prep or mobile phase preparation needs. So this is a great alternative. It allows you to, as mentioned, reduce the packaging and materials associated with shipping and disposal. They're in returnable containers, so the manufacturer is happy to take them back from you, take it off your hands, and reuse it as well for future purposes. And with respect to minimizing those single-use glass bottles in your lab, it does introduce an increased safety aspect. Hence, there are less interruptions that may occur in your lab, hence more productivity for your assays. So there are other alternatives. For example, instead of ordering your single-use water bottles, you can, if your lab already doesn't have access to it, a single-use water to a water purification system. So if that's already in your lab, that's great, and it's a great alternative to ordering HPLC grade water in that single-use glass. You can also think about aluminium containers, which are available in 10 and 28 litres to instead of your single-use glass bottles. And I do want to mention, for all of these alternatives, they are available in that high analytical grade that you require for either your HPLC or your LCMS assays. They come with the same high quality and the long-term batch-to-batch reproducibility, so you have the confidence for your assays to be repeated in the long term. And at the moment, we have these 5 different grades available in this returnable stainless steel barrel. And with that, I'm going to switch gears. We're going to now focus on the column selection. And by doing so, we always have to, it's a classical way, and I think it's the most elegant and information-rich way of looking at column selection, as well as guiding method development decisions. So these Van Diemter curves, as you can see in this black line here, we represent on the y-axis a performance indicator, and here we've got the height equivalent to a theoretical plate. You can also use the reduced H value. So when we speak in terms of H, the lower the value, the better column performance you achieve. And on the x-axis, we just simply systematically change the flow rate, the velocity with respect to linear velocity or reduced linear velocity. So slower flow rates to the left and higher flow rates, faster analysis, high throughput environments would want to choose flow rates to the right of this graph. What is really nice about this is for each of these data points, we have information not only about the velocity, the performance, but also the column characteristics. For example, the different paths the analyte has when it traverses the column, the dispersion in the axial or longitudinal way when it moves through the column, as well as the mass transfer kinetics with a C term, as the analyte mobile phase and stationary phase, the mass transfer kinetics between them all during the separation. So before I jump into some results, I do want to touch on the superficially porous particle technology, because for me, it's a really important tool for us to consider with sustainability. These are also known as fused core, core shell, core enhanced, partially porous, solid core, or with its initially coined term, pellicular particles or pellicular phases. And it's really good, if you don't already have that visualization of that particle architecture, to see this and its differences with a fully porous particle. So a fully porous particle, the analyte and mobile phase can access every part of that particle. However, with this SPP technology, there is that impermeable solid core. So that does restrict, and the analyte does have a shorter diffusion path length as it diffuses into the particle and out of it. So impermeable solid core that is surrounded by a porous aspect of the particle. We do need porosity. We need a space for the separation to occur, for the analytes to have a loadability, and also for interactions and separations to occur between specific analytes with either degradants or other analytes in the sample matrix. So the porosity is important. So another aspect that is really good to understand fundamentally is this rho value. So understanding this numerical value, you can already have a feel of the solid impermeable region, the ratio of that with respect to the total particle diameter. So a very brief historical snapshot to really demonstrate that this is not a new technology. In the 1960s, Csaba Horváth described the concept of this pellicular particle. And in the 1970s, the first generation of these phases were launched. So definitely not a new technology. It's been around since the early days. So that impermeable core region, that is what gives the benefits for higher column efficiencies at very fast flow rates and the reduced back pressure advantages. We do need that superficial porous layer. We do need it. And with respect or compared to totally porous particles, it does have a reduced loadability because of that impermeable region. And with that being said, there's also a reduced hydrophobicity because not all of that particle is porous. So to summarize the sustainable and performance advantages, they're really great tools for fast method development. And you can use these tools, great tools that can be used with your standard 400 bar systems. They can also be used with the UHPLC systems as well. Because of those back pressure advantages, there is a slower rate of degradation of the moving parts and the seals in your systems. And because of the higher efficiencies, you do have more to trade with respect to column performance, and you have the option to reduce that column format and operate in a more sustainable fashion. And the operation of those smaller column formats allow you to reduce the mobile phase solvent consumption and waste production associated with that. One more aspect before I move on to the results is it's really nice to look at this graph because it does tell you a bit more about the differences between totally porous and superficially porous particles. So if we look at this graph on the y-axis, we've got the volume fraction of porous material. So as we move up to the value of 1, we represent a totally porous particle. And on the x-axis, we have that rho value. So as we move to the value of 1 on the x-axis, we have a totally non-porous particle for the analytes and the mobile phase. So there is an optimum shell thickness around that solid core, and it's a different rho value as represented here for different SPP particles, and it will always be a compromise. And in the fields of chromatography, there's always compromises, but it's always a good approach to understand those compromises. So with respect to totally porous particles and superficially porous particles, there will be a compromise between efficiency, loading capacity, and analyte retention that's related to that superficial porous layer. However, they're great tools because once you understand those trade-offs, they're great tools to create fast assays, to increase the productivity of your lab. And on a per injection basis, if you can get through your samples quickly, shut down the system at the end of your sequence, your lab then consumes less energy. The operation of the smaller column formats, less solvent is used, and because of that back pressure advantage, you've got less frequency of your maintenance and less downtime for your systems. So let's jump into some results where we look at really small formats. So all of these different Van Dieter curves are going to be representative of fully porous particles in blue, and in green, we've got the superficially porous solid core technology. They're all packed in a very small column format. So a 5 centimeter in length column in a narrow bore ID of 2.1 millimeter ID. I do want to shift our focus closer to the 5 micron trends or Van Dieter curves, and you can see that across all the different velocities, the 5 micron SPP solid core technology has a significant gain in column performance with that reduced HETP term. Now I'm going to shift your focus from the 3 micron fully porous to the SPP 2.5 micron curve. And you can see that same trend holds true. It's not as significant, the gain in performance. However, the gain in performance is still there. Now I'm going to shift your focus to the 2.5 micron SPP column to the UHPLC type column with a sub 2 micron particle, fully porous. And you can see that now there's a similarity in the performance with even a crossover point happening down here. And that really shows you the comparable performance of that SPP column technology with the UHPLC column. But to highlight the back pressure advantages, we've earmarked the 400 bar limitation, which is exceeded very quickly at a lower velocity for the sub 2 micron column than it is for that SPP solid core 2.5 micron, where the 400 bar limitation is not exceeded until we move really to a faster velocity. So just reiterating, going through the performance and sustainability opportunities, you can reduce your column format and still achieve really good efficiencies that don't compromise anything. And these smaller column formats allow you to allow the manufacturer to reduce the stainless steel and stationary phase materials used. You can decrease the solvent use. You do not need to operate at Pmax or the fastest velocity. You can make a choice towards the left of this graph to operate at a slower velocity and decrease that waste production. So on a per injection basis, again, you can decrease the analysis time with these column formats and a faster velocity. If you shut down the system after the sequence is completed, you reduce the energy consumption, and specifically related to the SPP columns, lower back pressure, slower rate of degradation with respect to the seals and the moving parts, and also a decreased frequency with the maintenance. Because we are talking about smaller column formats, it is important to talk about system dispersion and its effect or impact on the column performance. And here on the y-axis, we have the percent of theoretical column performance obtained. And on the x-axis, we have the variance that's related to your system. So a very low system dispersion represented by UHPLC system. We increase the dispersion, but we can optimize our HPLC system and we work in this range. Or we've got that conventional 400 bar system, which of course has the larger variance or system dispersion compared to these two different systems. So on the x-axis, we increase the system dispersion as we move to the right. So you can see for all of these different column formats, very small column formats as well, you can see that for all of them, you lose your theoretical efficiency obtained. You lose your separation power of your column with more system variance introduced to the separation. So that's true, and it's most pronounced for the smallest column format, which here is represented by the 1 centimeter narrow bore 2.1 millimeter ID, and it's true for all of the trends. So it's good practice to always minimize, and it's the easiest one to attack, the post column dispersion. So that's the connection tubing connecting from your column outlet to the inlet of your detector. So minimize that connection tubing with respect to the diameter, internal diameter, as well as the length, in order for you to maximize your separation performance that's gained by your column. With that being said, there are still, and it's a really great tool when you do rely on the resolution power of your mass spec, you still will always benefit with a good LC strategy before that detection technique. So we know there's a need, and we have a tool in our portfolio that addresses that, and that's our high throughput or HTPMS column, which is really small, a 1 centimeter in bed length of this cartridge, and it's 2.1 millimeter ID, and it's within this hardware, and it's packed with 2 micron particles. It has an upper limit of 1000 bar. And I do want to stress that you should operate always in a grounded and a safe, electrically safe environment. So make sure if your iron source allows you for it, you can directly connect to it. Or if not, please still minimize that post-column dispersion in order for you to maximize the separation strategy before the mass spec detector. Each of these cartridges are individually QC tested, and because we're working in a really fast and rapid high throughput environment, please, when you operate these columns, make sure you toggle with your detector settings, input a really fast sampling rate and dwell time, because you need enough data points across these really small peaks. in order for you to still satisfy your quantification purposes. In these series of peak illustrations on mass spectra, I do want to show you the effect of the length of tubing because, for example, I did say you can't directly connect to your ion source. That's okay. And we'll see the peak shapes in these next series of images. So here we've got the cartridge or the HPMS column connected before that diversion valve that diverts to the ion source. So you can see some tubing is required, some dispersion has to be introduced. And we start off with a length of 26 centimeters for that tubing for 3 different analytes. And here we move to a much larger length of tubing, 55 centimeters. And you can see if we zoom in really deeply to the baseline, you can see the peak starts to disperse and broaden. But it's more pronounced, the dispersion effects, when we look at a really long, excessively long 80 centimeter length of tubing. And this might occur because there are some setups where the column compartment is quite far away from the mass spec detector. So I do emphasize bring those two, marry and hyphenate them really close in distance in order to avoid this dispersed, broader peak. You're always going to benefit by minimizing that length of tubing, increasing that peak height, narrowing that peak width in order to get the best resolution of your front end LC strategy as well as your mass spec strategy. So with that, let's look at some really nice case studies and examples of translating your original methods to sustainable ones, as well as looking at our portfolio and looking at some really nice examples and applications of sustainable methods. So the first one, we're looking at an isocratic assay with fully porous particle technology, and we're looking at UHPLC or HPLC sustainable alternatives. So the original method is showcased here. We've got a C18 type phase, a long 15 centimeter in length column, a typical analytical scale ID of 4.6 millimeters, using that conventional 400 bar system. Typically, these methods are used at 1 mil per minute. It's not uncommon to see, and they typically take 30 minutes to complete. So taking this as a case study, 35 mils of mobile phase is used per injection. As we move to the left of this slide, we look, and I do want to highlight as well, please use our method translator. We've got a really good tool that is freely available, and it allows you to computationally arrive at a column selection decision as well as the method parameters to quickly arrive at a new method. And we use that to create this new translated UHPLC assay. So we reduce the column format with the length and internal diameter, and also reduce that particle size. The sub 2 micron UHPLC column, you do need that UHPLC system to run, but the advantages for sustainability are worth it. For example, you can see this original assay translated to a UHPLC environment. Only 5 mils of mobile phase is used in comparison to 35 mils for the original assay. However, there are case studies, and it's not uncommon that UHPLC is being used. So we still have a HPLC system available. We can still turn that into a more sustainable method with our column selection choice. So simply looking at a smaller column format with respect to the column length as well as the internal diameter compared to the original method. This assay, you can see it's consumed 10 mils of mobile phase per run compared to 35 mils. So it's great. It's still a smaller column format, and you still translated that original method with your column selection choice. So this next case study, we're looking at gradient separations, again with fully porous particle technology. And here we have our original method, 15 centimeter in length, 4.6 millimeter ID, C18 type phase. This method requires 54 mils of mobile phase per injection. That's including the re-equilibration time of 20 column volumes. We can translate that into our UHPLC environment, smaller column format, 5 centimeter by 3 millimeter ID. we need to use that UHPLC system, but the benefits again are worth it. 7.2 mils of mobile phase is used per injection compared to 54 mils of that original assay. And you can also see the time frame of that one assay. You have many repeated injections in that same time frame. Moving over to the right, we've got a HPLC choice. Again, utilizing that same conventional 400 bar system. If that UHPLC system is not accessible, we can reduce the column format with respect to the length and internal diameter to 10 centimeters and 3 micron. And for each of these injections, only approximately 15.5 mils of mobile phase is used compared to the original assay. Great for sustainability and also complete multiple repeated injections in the same time frame of the original method. Just reinterpreting that information from the past 2 slides. So 2 slides away in the isocratic environment and also the gradient translations. This was really nice and I really liked it when Mark and Matt shared this. It's a really nice way of reinterpreting that same information, but for each of these bar graphs. So on the top, we've got the solvent usage in green. In the middle, we've got the total runtime in blue. And on the bottom, we've got the energy consumption in red. So for all of these bar graphs, we've got the original method, which takes the most or is the longest bar graph. We've got that optimized HPLC column selection decision, and you can see it's significantly lower than the original method. And the smallest is always going to be for that reduced column format UHPLC column choice, which you can see is the smallest bar graph for all of these. This is based on experimental data for 10 repeated injections, and we simply multiplied that by 10 in order to create this visual graphic. So in the slides to come, or following this, I am going to switch gears. We are going to be looking at comparisons of fully porous columns on the top and the chromatograms. And on the bottom, we will see this superficially porous solid core chromatographic data and separation profile. So here we start with an isocratic aspirin assay. We have the same bonded C18 type chemistry. We've got the same column format, 15 centimeter by 4.6 millimeter, and we've got the same particle size. The only difference here is the particle technology, and you can visually see here the reduced hydrophobicity characteristics because we don't have all of the porosity compared to the fully porous particle when we look at the solid core. So we've got the reduced hydrophobicity, but that's okay. From the perspective of sustainability, we've got a faster assay. And not only that, the peaks from comparing the top to the bottom separation profiles, the peaks are more Gaussian, they're more smaller, they're more narrower. And this is great, great column performance. So on the top, takes 20 minutes for that last eluting peak to come off. We've got the performance metric in plates per meter, 10,000 for the FPP column. For the SPP column, it is a faster assay, 10 minutes for that, lower than 10 minutes for the last eluting peak, 20,000 plates per meter for that last eluting peak too. So 50% faster assay with SPP column choice. 50% less mobile phase solvent is consumed, and you can visually see the narrower peak widths, which is an increase in column performance. And the only change here is definitely the particle technology. And if you look closely at the method is still the same. We did have to reduce the injection volume because of that reduced porosity for that SPP column. So let's look at another method translation example. Again, isocratic, fully porous to SPP, solid core. And the original monograph here, we've got 3 peaks obtained with a C18 type phase, 30 centimeter in length and approximately 4 millimeter ID internal diameter. For our SPP column, we've got our ultra core column, a reduced length. We still have an analytical scale ID and a C18 type phase. We still keep the mobile phase method composition fixed. We do translate the flow rate to a bit faster and again, reduce that injection volume. However, it's great because, as you can see, 7.5 minutes for that assay to be completed for the fully porous particle column, 7.5 mils of mobile phase consumed. And for the SPP column choice, we've now reduced that assay to 2 minutes and only 2.8 mils of mobile phase consumed per injection. So making a simple change with your column choice, you can create sustainable methods, 73% faster in this example, 63% less solvent, and increase column performance, which again you can visually see with the narrower, more Gaussian peak shapes for the SPP column. Now let's look at gradient separations. This is acetaminophen being separated, and again, the same bonded chemistry, the same column format, the same particle size. We are just looking at different particle technologies. And you can see on the top, it takes longer, 25 minutes when we earmark from the re-equilibration stage, 25 mils of solvent is used. And for the gradient separation of SPP particles, 20 minutes and 20 mils of mobile phase consumed. 20% faster for the solid core column, 20% less solvent. And what's really nice is even with gradient compression, with the gradient mobile phase peak compression, we still have an additional compression of the peaks with the SPP columns, which you can see with the thinner peak widths. So increased column performance with SPP columns, even in gradient separation conditions. Here we look at an example or same case study, looking at the same original monograph as the previous for the fully porous particle, and we trade some efficiency for higher throughput. And we do that by reducing that column format of the SPP column, the length, the internal diameter, as well as the particle size. Here we're actually taking the E mark after the last eluting peak. So it's 19.5 minutes and 19.5 mils of mobile phase solvent for the FPP column. The SPP column, 7 minutes with 3 mils of mobile phase consumed. Again, with all of these examples, we do use and exploit the use of the free method translator tool, which you can find on our website. So SPP, solid core technology, great, 64% faster, 85% less solvent consumed, and similar resolution. If I just highlight to you all here, the resolution for the top is 2.09 and the resolution of 2.08 for the closely eluting peak pair. So again, taking the same example of the previous slides for the fully porous particle packed column, here we do trade some more efficiency for higher throughput. We still have a bit of resolution to play around with our SPP column. So we simply just double the flow rate or double the velocity of the method with the same solid core column as shown in the previous slide. So the same mobile phase composition is going to be consumed, but we have decreased the time frame to 3.5 minutes. And it's great because taking a closer look, you can see resolution of 2.09. So it's matched the same separations, same selectivity for the critical peak pair. So again, solid core column, great for sustainability, 82% faster in this example, 85% less solvent, and the same resolution. In this example here, we're going to look at the application and a relatively larger molecule separation of the analysis of BSA tryptic digest. And this example actually showcases you where the sample's peak capacity exceeds the peak capacity of the column. So we definitely need to maximize the peak capacity of the separation strategy, but it's impossible. There's a lot of peaks there for that LC assay to completely resolve. However, I do want to emphasize here in these series of chromatograms, the effect of reducing the internal diameter only. So we've fixed the column length to 15 centimeter, we've fixed the column particle technology to solid core, and we fixed the particle size. So we're seeing the effects of 4.6 millimeter ID on the top. In the middle, we've got the 3 millimeter ID separation, and on the bottom, the 2.1 millimeter ID separation. We have translated and adjusted the flow rate accordingly. And in these highlighted boxes here, you can see the differences of the solvent consumption per injection. So from 4.6 to 3, we've saved about 60% of solvent, and from 4.6 down to the 2.1, we use 80% less solvent per injection. And in the next series of slides, I'm not going to be comparing anything. I'm just highlighting some really good examples of the final column selection choice and the final method development or parameters already finalized, and showcasing you some really nice applications that are in alignment with sustainability. So here we've got, again, a really complex sample. The peak capacity of the sample exceeds that of the LC column. Hence, you do need to hyphenate it with a mass spec strategy. So you can see here we separate 300 different contaminants in this separation space. We use a product from our ultra core range, the SPP column, 15 centimeter in length, 2.1 millimeter ID, 2.5 micron particle size, and only 8 mils of mobile solvent is used per injection. Here we look at relatively larger molecules with a separation of 4 peptides. We exploit the performance of an ultra-core biocolumn in a 15 centimeter length narrowbore ID and a relatively larger particle size, but still great for offering good column performance and offering a sustainable assay with only 3.2 mils of mobile phase consumed per injection. Another application, which is actually a really hot topic for pharmaceutical industry at the moment, which is the example of nitrosamines. And here we've got valsartan spiked with nitrosamines, and making this column selection decision with SPP from our ultra core range, C18 type column, 10 centimeter in length, narrowbore internal diameter, and relatively larger particle size, but still smaller compared to 5 micron, but larger compared to the 2.5. It's great. It still satisfies the application with only 3.5 mils of mobile phase solvent used per injection. Here we've got the high throughput MS column. Great. It's 1 centimeter in length, narrowbore ID, 2 micron particles, fully porous particles, and it's able to separate 26 illicit drugs in water in under 4 minutes, which is really great, and only 2 mils of mobile phase used up per injection. I'm systematically decreasing the mobile phase per injection for all of these applications. And here's a really nice application of that high throughput MS column, which in a sort of clinical space where a lot of samples need to be turned over. So with this, we've got drugs of abuse, specifically 16 analytes in 1 minute in a really complex sample matrix. And each assay is completed in 1 minute, only 1.5 mils of mobile phase is consumed. If we showed the TIC, it would have been messy because the sample matrix is inherently messy. So of course, mass spec, it gives you the great choice of looking at the extracted ion chromatogram, and we show it for the first and last eluting peaks. And you can also see the really good calibration data for these drugs of abuse in plasma. And the final application, again, highlighting the high throughput capabilities of this column. You can still have a great separation strategy before your mass spec jumps in, and that's with that HTPMS column. The final application, immunosuppressants in under 1.4 minutes and only 1.2 mil of mobile phase consumed. And with that, I hope that it's clear that there are ways to align your LCMS workflows to more sustainable ways. And there's not enough time to fit it all. So I hope this presentation really opened your mind into integrating new or alternative choices for your solvent management decisions, as well as your column selection decisions, specifically those reduced column formats, either in the fully porous or the superficially porous particle technology. And before I end, I do want to highlight that we've got really great technical content in our website that's freely available. We've got a really great team of scientists, a great team of people at Avantor that's continuously updating and generating up-to-date information, for example, white papers, knowledge notes. We've got different marketing literature and also that method translator tool. There is a how to use guide as well as a link to download it. And also, please feel free to reach any one of us. We're we're enthusiastic as well as more than happy to help you create more sustainable assays. And looking deeper into that method translator tool, you can see it's a computational strategy. You can enter different details of your original method and your new method, and it does very quickly calculates for you. For example, in this example, the new method allows you to save 86% of your solvent. So please check it out, download it and use it, exploit it, and create more sustainable assays. I know I didn't spend too much time on the mobile phase solvent, so please feel free to contact us. We've got literature to highlight the use and the different products we have to align your solvent management decisions with sustainability. And with that, I'd like to thank you all for your time, and also please feel free to reach out to one of us, our whole team around the globe. We're all very enthusiastic and very friendly, and we are here to help you with all of your chromatography problems as well. And it doesn't necessarily have to be our products. We're always happy to help with any chromatography related problems.
Okay, thank you very much, Arianne, for that. I think we'll call it a whirlwind tour of sustainable choices that can be made in chromatography. So, as I'd say, the question box is there, so please feel free to add your questions. We have a remaining 13 minutes for the Q&A session. I've got a couple of questions I'd like to start with from the box. So you didn't go into alternatives to acetonitrile, but what options are there? Because obviously that's one of the solvents that are of concern.
Yes, I think the one that always pops up straight into my mind is IPA. However, when that pops up in my mind, there's also that game of compromises. So IPA, definitely a different organic strength, and also you're going to have a different viscosity profile. It's actually more viscous than acetonitrile. So make sure you can have that back pressure to play with. Also, you can use heated water, and there's all different alternatives. It's definitely something that you can jump into the literature to look at. And definitely with a stronger focus with sustainability, there's going to be a lot more literature that's going to be applicable to your methods. So yeah, IPA, heated water, you can change the mobile phase, but definitely look at the compromises that you make, because it is a change and you may have to revalidate or start from scratch and develop a new method. But it is worth it, because definitely shown with a few examples here, you might not only save with respect to solvent, but also with time and increase the productivity of your lab.
Perfect. So there's one here with respect to smaller column formats. Does system dispersion negate the effects, and is it easy to address?
Yes, is the answer. It always is, as you play around with that ratio. If you play around with the ratio of your column volume and the system dispersion volume, if you reduce that column format and make that volume smaller, then if you fix that system dispersion and play around with that ratio, it will have a bigger effect to your column performance. And that was shown earlier in the column selection graph here. So definitely minimize that dispersion as much as you can. And the easiest one to approach is always going to be the connection tubing that's connecting your column outlet to the inlet of your detector. And I have been in environments where we sometimes, even in a QC regulated environment, we've actually changed the stack formation. So where the column compartment sits, we've created the other side of the stack. So in alignment with that is the detection compartment. So that allows you to create a linear, short distant connection with your connection tubing between the column outlet to the inlet of your detector in order to address this slide right here to maximize the separation performance gained by your column. You don't want to compromise it with introducing system dispersion and that giving those peaks or even too closely eluding peaks any space to redisperse into one another. So attack the post-column dispersion. It's the easiest one to do.
Thank you. I think one more. There's a focus on the 2.1 and the 3.0 mils in terms of column IDs. What comments do you have on smaller IDs such as 1.0 or 1.5 millimeter?
I think it is important, and I know that some assays do require a smaller internal diameter and even pushes down to the realm of capillary scale chromatography. However, if you look at this graph as well, it's lucky that I'm still on it. We've got the same fixed length and we've got the 4.6 millimeter ID. We've got the 3 millimeter ID, 2.1 millimeter ID. And you can see that trend moves down. So you lose theoretical efficiency, or you lose your separation power of your column as you reduce that internal diameter. And that's mainly the dispersion that's associated to the column wall. So if you've got a larger tube, the wall effect is not as prominent, but as you make that tube smaller with respect to the internal diameter, there is going to be dispersion associated with the column wall effect. And also you have to operate in this sort of region with those types of columns. You have to have minimized not only in the post column, but also in the pre-column system dispersion. You need to minimize that system dispersion as much as you can when you operate those smaller column formats with respect to the internal diameters of 1 and 1.5. Thanks for the question. Thank you to all the questions.
Just trying to see if there's anything else coming through. Please remember to put your questions in the chat or in the question box. One more. Why is the C-term not as flat for the SPP curve shown in the column selection section?
That's a very good question, and I think this is one thing that I also thought about when initially looking at the data. However, one thing that we do need to appreciate here is we are operating in a very small column format, so there is more effect from the system dispersion. We can't optimize at all times, so that rate of increase, the slope is still much lower with respect to the C term compared to the particle size in the fully porous. it is a slower rate of increase, which does show you hints that the C term is flatter, but I'm guessing here there's going to be influences from the system dispersion. And I also know I have had experiences where I've actually introduced dispersion by overloading the column. So that also influenced the C term in my Van Dienzer curves. So if you've got a theoretically beautiful curve with no system dispersion, it would be great. But it is still a slower rate of increase or loss in performance at the higher velocity compared to its fully porous counterparts.
Okay, I hope that answers the question. I don't see any further questions currently in the box. Okay, if there's no further questions, we'll let you get a couple of minutes back in your day. Thank you everybody for joining. We hope that you found this incredibly this extensive talk incredibly useful. If you do have any questions following the session, then please feel free to reach out at webinar@avantorsciences.com or to our technical team, so you can reach out to chromesupport@avantorsciences.com. Thank you, and please keep an eye out for any our future webinars as well. Thank you.